Pre-statistics. Using exponential functions to model data. Lesson objective. Find an exponential model by using the base multiplier property. Lesson objective. Definition. An exponential model is an exponential function or its graph that explains the relationship between two quantities for an authentic situation. If all the data points for the situation lie on an exponential curve, then we say that the independent and dependent variables exponentially related. If no exponential curve contains all the data points, but the exponential curve comes close to all the data points, and perhaps containing some of them, we say that the two variables are approximately exponentially related. Example 1. Suppose a peach has 3 million bacteria on it at noon on Monday, and that one bacterium divides into 2 bacteria every hour on average. So here's a visual. We have one bacterium, and in 1 hour it splits into 2. Then an hour later, this one splits into 2, and this one splits into 2. The next hour, this one splits into 2, this one splits into 2, this one, and also this one. Let B be the number of bacteria in millions on the peach at T hours after noon on Monday. So our independent variable is T, the number of hours after noontime on Monday. Number 1. Find an equation of f. Solution. We first want to create a table with the assumptions. So at 0 hours, when t is 0, we have 3 million. 1 hour later, it doubles. 1 hour after that, it doubles. Then it doubles again the next hour, and then the next hour. So as t increases by 1, f of t changes by multiplying 2. It doubles. So the model is in the form f of t equals a times 2 to the t power. So the intercept is 0, 3, because when t was 0 we had a y value of 3. So our function is f of t equals 3 times 2 to the t power. We can verify this using the graphing calculator. We see our table matches the table we constructed. Here's the graph. So number 2, predict the number of bacteria on the peach at noon on Tuesday. Solution. Well, this is exactly 24 hours since noon on Monday, so t is equal to 24. So if we substitute 24 for t, we have f of 24 equals 3 times 2 raised to the 24th power, which is equal to 50,331,648. So according to the model, there would be 50,331,648 million bacteria. Now if we drop the million, it turns out there would be about 50 trillion bacteria at noon on Tuesday. Modeling with an exponential function. Summary. Exponential function y equals a times b to the t power has the y-intercept at 0, a. Y is a quantity at time t, and a is a quantity at time t equals 0. We can think of this as our initial value. This is what we start with. Example 2. A person invests $5,000 into an account that earns 6% interest compounded annually. Number 1. Let v equal f of t be the value of the account at t years after the money is invested. Find an equation of f. Solution: each year the investment value is the previous value, which is 100%, plus the 6% of the previous value. Each year the investment is 106% of the previous year because we take the original amount plus 6%. As t increases by 1, the value of v is multiplied by 1.06. 1.06 is the same thing as 106%. Because the value started at 5,000, a is equal to 5,000. So here's a table of values. When t is 0, our initial starting point, we had 5,000. 1 year later, we have 5,000 plus the 6%, which is 5,300. The next year, we have 5,300 times 6%, and we have 5,618. The next year, we have 5,618 plus the 6%, so on and so forth. So f of t equals 5,000 times 1.06 raised to the t power. Number 2, what will be the value after 10 years? Solution: we substitute 10 for t. So f of t is 5,000 times 1.06 raised to the 10th power, which rounded off to the nearest penny is $8,954.24. So this value means if you put $5,000 in a bank that draws 6% compounded annually, in 10 years you'll have almost $9,000. Thanks for watching.